All right, we're getting to that point of organic chemistry where you just got to complete the reactions. And so in order to complete the reactions, you have to know what each of these reactions and reagents does and how that affects the mechanisms in some cases. Okay, let's just go one at a time. We've got a sodium cyanide, and the cyanide is only acting as a nucleophile. I've got a leaving group in the secondary position, but I've also got a polar aprotic solvent. So that'll promote an SN2 reaction. So that's one of the other things it wanted me to write down. SN2, what reaction mechanism will it follow? So now that I've done SN2, I need to write the products. And so writing the products means I need to remember the stereochemical outcome of the reaction. And then the stereochemical outcome of the reaction is that there is an inversion in stereochemistry. And so the cyanide adds, but it's now facing a different direction. Okay, for tertiary potassium tertiary butoxide, it's a strong base, but the leaving group is in a tertiary position. So I want to consider both of those factors. Even though it's a tertiary position, I've got a strong base and a strong nucleophile. So the E2 reaction mechanism is predominant. So I've got E2 as the reaction mechanism. And so that means I'm going to form a less steric, I'm going to form the less substituted product because of the bulky base. There will be a minor product that is the more substituted double bond. And that looks like this. So here's the major product, here's the minor product. All right, what about the next one? It looks like I've got a primary position for the leaving group and only a nucleophile. So again, this would be SN2. And so I've got a 6-membered ring, 1, 2, 3, and now have replaced or substituted the Br for the SH. That's not a stereo center, so I don't need to worry about it. Okay, the next one is a little bit more of a challenge. I've got a leaving group in a tertiary position, but I've got a weak base and a weak nucleophile as the reagent. And so what that means is that I have a pretty good competition between SN1 and E1. So I've got SN1 and E1 happening. And so remember that there, since it's going to be unimolecular, the unimolecular reaction will form the cation and then the reaction proceeds. If the substitution reaction proceeds, then it's going to substitute. If the elimination reaction proceeds, then it's going to eliminate. Okay, for the elimination products, I can form a double bond here, but I could also form a double bond there. This one, of course, will be the major product because it's more stable. And then for the elimination, for the substitution reaction, I'll have another major product where I have an OET that forms here. Now, I don't have to consider an enantiomer because that's not a stereo center. Okay, what about the next guy? I've got a strong base and I've got a secondary position for my leaving group. And so I'm still going to have some competition between E2 and SN2. But the E2 is going to be favored. And so when I consider the E2 product, that means a double bond would form here. So this is definitely the major product. But I'll also have a minor E2 product where the double bond forms here. And I'll also have a minor substitution product But remember, it's still SN2, so there's going to be an inversion in the stereochemistry where the ethoxide substitutes for the bromine. So I've got two minor products and a major product. This is the SN2 product, and these are the E2 products. All right, what about the next one? Well, in the next one, I have exactly the same situation. Sodium methoxide, strong base, strong nucleophile, and I've got a leaving group in the secondary position. So I'm going to have both a substitution product and I'm going to have an E2 product. So let's take a look at the E2 product, the substitution product first. I know that that's going to be one of the minor products. So I'm going to have no change here in the stereochemistry. But I'm going to have an inversion in the stereo center here. So in order to make sure that I have an inverted stereochemistry, I would look like this. Okay, so that's my SN2. It's minor. And now what about my E2 products? Well, I have another minor E2 product where the least substituted double bond forms. And so that looks like this. That's another minor E2 product. And so what about the major E2 product? Well, the major E2 product would form between those double bonds, but I have to look at that beta position. And in that beta position, I only have one beta hydrogen. So I have to take a quick detour and I have to draw a Newman projection. And I'm going to draw the Newman projection looking down this bond. And so that means my Newman projection should be drawn this way for convenience. I have a 6-membered ring up here. And what do I have? The methyl group is going away from me. So when I look down that bond, it means it'll be over here on the left. I've got a hydrogen here. What about in the back? Where's the bromine? Well, I see that the bromine is also pointing in the up direction. So what that actually means is it means that I have a staggered conformation. So I have to rotate that bromine down. So if I start with a staggered conformation, it looks like this, where I've got the CH3, I've got a hydrogen over here, and then I've got my cyclohexyl group there. This one's going to be really a big mess because it's going to be really hard to draw that cyclohexane group. Here's my bromine. What do I have? Where's the methyl group? The methyl group is in the opposite direction as the other CH3 group. So that points it there. So how do I get this bromine to be anti-paraplanar? Well, that means I need to rotate this direction. So the bromine ends up being here. The CH3 ends up being here. The hydrogen ends up being here. That's where my double bond forms. And so my other product, my major E2 product, will look like this. I've got my double bond. And on the front carbon, I've got a CH3. And I've got a 6-membered ring. What do I have on the back carbon? Well, the back carbon, I have the CH3 group in the same direction as the 6-membered ring, the hydrogen in the same direction as the pointing in the same way as the methyl group. And so this is my major E2 product. Okay, so again, consideration of that anti-paraplanar transition state. Let me erase all this. Okay, now we can go back in here and take a look at this one. DBN, it's a base only. So let's take a look at the base only. Can't have a double bond that forms here because it's already got 4 bonds. So that means there's only one possible product. It's going to be a benzene ring here, and a double bond formed there. Okay, so what else do we have going on here? We've got the last reaction, which is DBU. Again, that's a base only. And so I want to look at the position of the leaving group. And the leaving group is the chlorine. And I need to look at the two positions that are beta from there. Well, the position at the top has a two methyl groups, so there's no hydrogen on the top, so I don't need to consider that one. The only one I need to consider is there's one hydrogen there. And so recall that if we were to think about the chair conformation of that cyclohexane, then we would have the Cl in this position, and we would have two different groups next to it. One of those groups would be the CH3, and it would point down, opposite of the Cl, which is pointing up. And so here's my beta hydrogen. That's my beta hydrogen. It's not anti-paraplanar from the Cl in this position. And remember that the E2 reaction can only take place. It can only take place when the hydrogen and the chlorine are anti-paraplanar. And the only time the chlorine can be anti-paraplanar is when it's axial. So I've drawn the conformation for the cyclohexane ring that has the Cl in the axial position. And I see that the beta hydrogen is not anti-paraplanar for it. Remember, these two groups are CH3 groups, so that's not going to matter. So what do I get? What's the answer here? No reaction. Okay, I know that was a lot of work. We had a lot of different reactions to consider, but this is what you need to be able to do in order to be successful in organic chemistry, especially when we're talking about organic chemistry 2. You need to be able to go through this, and essentially this maybe even a little bit faster than I did. Okay, thanks.